Make sure, yes, okay. So now we're going to talk about some trends in the periodic table. And one of them is atomic size. Well, to talk about atomic size, we have to talk about how do you define atomic size? Because as we've seen, an atom is not a little marble or a little billiard ball, right? It's got this nucleus, and then we've got these electrons that are in these weird probability things that look like crazy clown balloon structure stuff, right? So how do we define where's the edge of the atom? There's different methods. So one is called the non-bonding atomic radius. It's also known as the van der Waals radius. And this is half the distance between adjacent nuclei in the atomic solid. So here we have solid krypton, which, you know, you have to cool that down to a really, really cold temperature to get it to be solid, but it can be done. And so you look at the solid, and they use techniques like X-ray diffraction and different things like that to figure out this distance. But you look at the distance between the two nuclei, and you divide that in half, and you say that's the radius of the atom. So that kind of makes sense, right? So that's one way. Another way is to look at bonding atomic radius, or covalent radius. And so for nonmetals, it'll be half the distance between two of the atoms bonded together. So here we know that bromine forms a diatomic molecule. When bromine atoms bond together, we can measure the distance between the radii, and it's 228 picometers, so you cut that in half, and you say, oh, the radius of bromine is 114 picometers. Now, are you going to get the same result using both methods? No. No, you're not. For metals, it'll be half the distance between two of the atoms next to each other in a crystal of the metal. Well, that ends up being a lot more like this non-bonding radius, doesn't it? So those are two methods. So how are we going to talk about atomic radius? We're just going to use it in a more general term. Atomic radius is an average radius of an atom based on measuring large numbers of elements and compounds. So we're going to talk in general terms. There are certainly times, especially if you're doing research or looking at crystal structures and things, where you want to know more specifically what the atomic radius is. This atomic radius in the general way gives us an approximate bond length. It gives us a way to kind of estimate how long bonds are by just adding together the atomic radii of the bonded atoms. And this works for covalent bonds, doesn't work for ionic bonds. There are trends among the main group elements, especially for atomic radius, and we need to know how this works. This is actually similar to a graph that I make some of my Chem 3A students graph. We give them a table and we make them graph this as just sort of an exercise. And at first, if you look at this without the lines connecting it, it's like, wow, that's just a big old mess. How do you make any sense out of that? But we see there is a pattern here. Here's hydrogen and helium. Helium is smaller than hydrogen. And then there's this big leap to lithium. And then the radius goes down as we go across to neon. And then it jumps up to sodium, and then it goes down. And so there's these patterns. Here's the transition elements. They do this kind of loopy thing. They're just not real predictable for anything. And then it keeps going down, jumps up again, comes down. Little blip here with the transition elements. So these are all the alkali metals. And you see there is a general trend. It's not linear. But as we go down the period, lithium to sodium to potassium to rubidium to cesium, they're getting larger, right? And if we look at the noble gases, helium to neon to argon to krypton to xenon, it's not linear, but there's a trend. As you go down a group in the periodic table, the atoms tend to get larger. But as we go across, let's say from sodium to argon, they get smaller. Now, it's not absolute, like here there's a little blip. This one is smaller than the next one. But we're talking general trends here. As you go across a period in the periodic table, like period 3 from sodium to argon, the ones on the right are smaller. The first trend of atomic radius increasing as you go down a group makes lots of sense. Because as we're going down, the principal quantum number, n, is going up. And as the principal quantum number goes up, those orbitals are getting larger and larger. We're adding layers to the onion, if you want to think about it that way. So we're adding a layer, we're adding a layer, we're adding a layer. That makes sense that those should be larger. And you look at their masses, too. Lithium 6.9 to cesium 132. You expect the one with more mass to be larger. So that one's easy. The trend across, why? Why does it do that? The atomic radius decreases. So we saw the graph. Here's numbers. Here's sodium 186, magnesium 160, 143. They're just getting smaller and smaller. This is not what we expect. Because argon has a mass of 39.9, sodium has a mass of 22.9. We would expect argon to be larger, just based on mass. But what's happening with the atomic numbers, the principal quantum number? Sodium has its valence electrons in level 3, and argon also has its valence electrons in level 3. They are in the same principal energy level, the same layer of onion skin. So they're going to be roughly the same distance from the nucleus. So if we think about it that way, we'd say, well, they should all be the same size, right? Because if that layer, it's easier if you think about the Bohr model of the atom. And, sometimes it's just really helpful to think about the Bohr model of the atom. So here's the nucleus, and here's level 1, and here's level 2, and here's level 3. And so in level 3, all we're doing is we're adding more electrons in this orbit. Well, they're the same distance, right? So they should all be the same size. And yet it's decreasing.
Does that have something to do with that magnetic attraction and that penetration?
It has more to do with effective nuclear charge, the shielding. It has more to do with shielding. But penetration is part of it. So when we have a multi-electron system, as we talked about yesterday, we have these interactions between the electrons. And so the electrons are attracted to the nucleus, but they're repelled from each other. And these outer electrons are effectively shielded from the nucleus by the core of electrons, by the core electrons. And so this causes the outer electrons to not experience the full strength of the nuclear charge. So again, to go to the Bohr model, just because it's so much easier to draw. Oh, let's make our electrons red. Okay, so let's make this be lithium. So lithium has 2 electrons in the first level and 1 in the second level. And inside here, we've got a 3+ charge. This is lithium. So this electron on the outside, and this is just explaining it in very simplistic terms, is shielded by these 2 electrons. These 2 electrons essentially counteract 2 of the protons in here. Cancel it out however you want to think about it. So the effective nuclear charge that this electron sees is +1. So let's compare that to, let's do neon. Neon also has 2 electrons in the second energy level. How many does it, in the first level, how many does it have in the second? 8. 1, 2, 3, 4, 5, 6, 7, 8. Now this is the Bohr model. This is not actually how they do it, but it's easier to think about. What is the charge on the nucleus for neon? It's plus 10. Okay, so we still have 2 core electrons. So then what is the effective charge that these electrons are going to see? Plus 8. Does that make sense? So do you remember Coulomb's law? I forget if it was, I think it's just an E. It was Q1, Q2 over R times this constant. So, well, actually, let's just do it this way. It's proportional. The potential energy of attraction or repulsion is proportional to the charges on the two objects, and it's inversely proportional to the distance between them. So here, let's just look at charges. This electron is experiencing a +1 attraction. These electrons are experiencing a +8. Which is going to be more pulled in? Which is going to have a higher attraction? +8, right? It's like, is this a trick question? No, it's not a trick question. The effective nuclear charge for the valence electrons on neon is +8, and for lithium, it's +1. Well, greater attraction is going to pull those electrons in closer to the nucleus. It's going to contract the atom.
Is that what gives it its stability?
That's not what gives its stability, but it's why neon is smaller than lithium, even though lithium has fewer protons and electrons than neon does. Neon's got 10 protons and electrons. Lithium only has 3. We would expect, just, because bigger, you got more pieces, you expect it to be larger, right? But it's because of this difference in effective nuclear charge. These, as we go across a period, what we're doing is we're adding valence electrons in the same energy level, roughly the same distance from the nucleus.
You have more mass on the outer shell, traction, they would just...
Well, more mass, it's really about the charge.
Yeah.
So R doesn't really play into this. The electron is always +1, but the other charge that's attracting it is the charge of the nucleus. And then shielding plays into it. And so here we have, these are shielding this electron. I don't know, it's like you've got 2 people in front of the TV and they're dodging around so that you can't see what's on the television.
So what are Q1 and Q2?
Q1 and Q2 are the electrical charges on the objects you're talking about.
So they're 2 different atoms?
It's an element. I'm sorry, in this example, it's a nucleus and an electron.
Okay.
So here, this nucleus has a +3 charge, but the effective charge for this guy is 1+. He has a 1- charge. And over here, let's look at this guy. He has a 1- charge. But the effective charge that he's seeing is +8. So energy is proportional to the 1 times the other. So here we have 1 times 1. Here we have 1 times 8. Those are rough numbers, approximations. So as you go across a period, the effective nuclear charge on the nucleus increases. Of course, it's nuclear on the nucleus. The effective nuclear charge increases. And so the force of attraction between the nucleus and the electrons increases, and that pulls them in tighter. And so as you go across a period, the atoms get smaller. Does that make sense? Does anybody have any questions? We've got some other trends, and we need to be able to predict, by looking at the periodic table, which one's smaller. The going down business is fine. The going across, we're going to have multiple trends, and it's all involved increasing, decreasing, up and down and across. And for me, the only way I can remember it is to think about why. And, sometimes it takes a few minutes. Well, maybe not a few minutes, but, at least a minute or so, and you can reason it through. But it works every time, right? And otherwise, you might as well just be guessing.
And what did you call the effectiveness? What was that?
Effective nuclear charge. And that's due to the shielding. So, oh, look, yeah, I didn't have to draw those pictures. So here's lithium. +3 charge on the nucleus. We have 2 core electrons, and so they shield the valence electrons so that the effective nuclear charge is +1, and out here is our valence electron. So the effective nuclear charge is the net charge that's being experienced by an electron. And the way you would calculate that, if you like formulas, is you take Z, the actual charge on the nucleus, the number of protons, and you subtract the number of core electrons. And we learned yesterday how to identify which are the core electrons and which are the valence electrons. Valence electrons do shield each other a little bit, but it's not worth talking about. So, example, what are the effective nuclear charges of nitrogen and argon? So, nitrogen. How many protons does nitrogen have? 7. So it's got 7 protons. So its actual nuclear charge is 7. How many core electrons? Well, let's back this up. So it's got 7 protons and it's got 7 electrons, right? How many valence electrons does nitrogen have? 7. It has 5. We look at the periodic tables at group 5A. If it's got 5 valence electrons, how many core electrons does it have? 2. It's just the difference. So the number of core electrons is 2. So then the effective nuclear charge is 7 minus 2, or 5. So for nitrogen, Z effective, the effective nuclear charge, Z minus S, 7 minus 5 is 2. So then they're asking us about argon. So for argon, I'll do this in a different color. Argon. So the effective nuclear charge is the actual charge. How many protons does argon have? 18. How many electrons does argon have? 18. How many valence electrons? 8. So if it's got 18 electrons and 8 of them are valence electrons, how many core electrons? 10. The effective nuclear charge for argon is 8. Any questions?
So, do we always have to calculate it, or can you just say that Z effective is usually the number of valences?
Well, what I'm doing here is I'm showing you how you figure out what the effective nuclear charge is. And some of you may need to write it all out like this, and that is absolutely fine. Other people can look at the periodic table and figure it out, and that's fine too. This is not a situation where you absolutely have to show your work or prove how you got that answer.
How does it change D with D block?
With what?
D block?
We're not going to talk about the D blocks, the transition metals. Yeah. We're going to stick to the parts that are predictable. Any other questions? So, quantum mechanical explanation for the trend in atomic radius. Kind of already mentioned this, just because I couldn't help myself. When we're going down a column, the principal quantum number increases. As principal quantum number increases, the size of the orbitals increases. If the orbitals are larger, the atomic radius is going to be larger. Going across a period, the effective nuclear charge increases while the principal quantum number remains the same. Okay, you can't compare with effective nuclear charge things that are not in the same period, because then you're dealing with two factors. One factor is changing quantum number. The other factor is effective nuclear charge. So we compare effective nuclear charge in the same period. All those electrons are in the same principal energy level. So as we go across, the effective nuclear charge increases while n stays the same, and that results in a stronger attraction between the valence electrons and the nucleus, which pulls them in, and you get a smaller atomic radius as a result. Any questions? So what about the transition metals? Atoms in the same group increase in size down a column just like the main group elements. So if you look at, iron and ruthenium and osmium, osmium's going to be bigger than iron. When you're going across, though, the atomic radii of transition metals is roughly the same across a D block. On the graph, we saw that there was a little bit of a dip. Let me go back real quick there. So here in the green, we see that there's a little bit of a trend, but it goes down and comes back up, and it's not very predictable. All of these guys, these period 5 transition elements, are similar in atomic radius. So there's much less difference for them than across the main group elements. And that's because the valence shell is not those D block electrons. The valence shell is the S electrons. And the effective nuclear charge for all of those guys is roughly the same. There are differences, and we're not going to care about them. Okay? So we should be able to predict differences in atomic radius if we're looking at a period going up and down, a group going up and down, period going to side, it's kind of hard to predict because it kind of goes down and back up again. Okay, so what do you need to be able to do? Something like this. On the basis of periodic trends, choose the larger atom in each pair, if possible. So if we look at tin and iodine, we need to find their relative position on the periodic table. And it would really be helpful to actually have a periodic table here. But we find that, see, there's 1, 2. That here's iodine and here's tin. They're in the same period. They're in period 5 in the periodic table. So based on periodic trends, which do we expect to be larger?
No, 10. Sorry,
10. Yes. 10 is going to be larger. Because as we go across, effective nuclear charge increases while n stays the same, electrons get pulled in tighter. How about germanium and polonium? Let's see. If we put polonium down here, germanium would be right here.
So because they're not in the same period, we can't compare them?
Well, let's think about it. Because they're not in the same period and they're not in the same group, it gets a little tricky, right? So we're having opposing forces here. Here's germanium. We would expect size to go down as we go across. Polonium is to the right, and so by that trend, we'd expect this to be smaller. But then we also know that the radius increases as you go down, which would say that polonium should be larger. So, survey says, like if I was giving this as a written question, there are two answers that I would accept. I would accept we can't tell. I would accept that as an answer. Going a little further, which do you think is more significant? The change in effective nuclear charge or the higher quantum number? Higher quantum number. Higher quantum number, those orbitals are getting bigger. That's more significant than the change in atomic radius due to the effective nuclear charge. So I would also accept that polonium is the larger. Okay? Now, if I was giving this as a multiple choice exam, I would not list intentionally both of those. So I would not list that this could be and that it's not possible. Because then we get into the problem of having two correct answers. So I would accept either of those answers. Chromium and wolfram. Tungsten. So here's chromium up here, and here's tungsten down there. Which one's larger? Tungsten. Okay. Now, if you had elements on a diagonal this way, X and O, which one should be smaller? X. So the only time you can get away with we can't tell is if the trends are opposing each other. Any questions?